12.2 Two-way ANOVA Key Concept. This section describes the method of two-way analysis of variance, which is used with data partitioned into categories according to two factors. The method of this section requires that we first test for an interaction between the two factors. Then we test for an effect from the row factor, and we test for an effect from the column factor. The table below includes data of the measured force on femurs or thigh bones in car crash tests. The data are measured in kilonewtons. The table has data categorized according to the two factors. Number one, we have the femur side. One factor is whether the femur is in the left leg or the right leg, and this represents the row. The vehicle size category, which is the second factor, is the vehicle size category, which is small, mid-size, large SUV, and these are the columns. So the left femur and right femur represent the row factor. The small, mid-size, large SUV, since those are columns, that represents the column. Now, the table, again, is categorized with two factors. The table has 8 subcategories called cells containing 5 values each. One factor is the size of the vehicle, and the second factor is the femur side. Now, in analyzing the sample data in the table, we have already discussed one-way analysis of variance for a single factor, section 12.1, so it might seem reasonable to simply proceed with one-way ANOVA for the factor of femur side and another one-way ANOVA for the factor of vehicle size category. However, that approach wastes information and totally ignores a very important feature, the possible effect of an interaction between the two factors. There is an interaction between two factors if the effect of one of the factors changes for different categories of the other factor. As an example of an interaction between two factors, consider food pairings. Peanut butter and jelly interact well, but ketchup and ice cream interact in a way that results in a bad taste. So we rarely see someone eating ice cream topped with ketchup. In general, consider an interaction to be an effect due to the combination of the two factors. Explore data with means and an interaction graph. Exploring data in the earlier table, calculate the mean for each cell and construct a graph. Now, the individual cell means are shown in the table below, and those means vary from a low of 0.68 to a high of 1.02, so they vary considerably. So here are the means of that data. Now, we can interpret an interaction graph as follows. The interaction effect. An interaction effect is suggested when the line segments are far from being parallel. No interaction effect if the line segments are approximately parallel. It appears that the different categories of a variable have the same effect for the different categories of the other variable. So there does not appear to be an interaction effect looking at this particular graph. Now, instead of relying only on subjective judgments made by examining the means in the interaction graph, we will proceed with the more objective procedure of the two-way analysis of variance. Here are the requirements and basic procedure for two-way analysis of variance ANOVA. The procedure is also summarized in the following key element box. So for a two-way analysis of variance, objective. With sample data categorized with two factors, a row variable and a column variable, use two-way analysis of variance to conduct the following 3 tests. Number 1, you test for an effect from an interaction between the row factor and the column factor. Number 2, you test for an effect from the row factor, and number 3, you test for an effect from the column factor. Requirements. Number 1, Normality. For each cell, the sample values come from a population with a distribution that is approximately normal. Number 2, variation. The populations have the same variance or standard deviation. Number 3, sampling. The samples are simple random samples of quantitative data. Number 4, independence. The samples are independent of each other. Number 5, two-way. The sample values are categorized in two ways. And number 6, a balanced design. All of the cells have the same number of sample values. Here's the procedure for a two-way ANOVA. Step 1, the interaction effect. In two-way analysis of variance, begin by testing the null hypothesis that there is no interaction between the two factors. Use technology to find the p-value corresponding to the following test statistic. F is equal to the interaction divided by the error using the MS. Now, we reject the null if the p-value corresponding to the above test statistic is small, meaning less than or equal to the 0.05, reject the null hypothesis of no interaction, conclude that there is an interaction effect. Fail to reject the null if the p-value is large, greater than 0.05, fail to reject the null hypothesis of no interaction between the two factors, conclude that there is no interaction effect. Step 2, row-column effects. Now, if we conclude that there is an interaction effect, then we should stop now. We should not proceed with the 2 additional tests. Now, if there is an interaction between factors, we shouldn't consider the effects of either factor without considering those of the other. If we conclude that there is no interaction effect, then we should proceed with the following 2 hypothesis tests. Step 3, the row factor. For the row factor, you test the null hypothesis. There is no effects from the row factor. Find the p-value corresponding to the test statistic, which is the row divided by the error. Reject the null if the p-value corresponding to the test statistic is small, meaning less than or equal to 0.05. Reject the null hypothesis of no effect from the row factor. Conclude there is an effect from the row factor. Fail to reject if the p-value is large, greater than 0.05. Fail to reject the null hypothesis of no effect from the row factor, and then conclude there is no effect from the row factor. Step 4, column factor. For the column factor, test the null hypothesis, where there is no effects from the column factor. Find the p-value corresponding to the test statistic, where you have the column divided by the error value. Reject the null if the p-value corresponding to the test statistic is small, again less than or equal to 0.05. Reject the null hypothesis of no effect from the column factor, and then conclude there is an effect from the column factor. Fail to reject the null if the p-value is large, greater than 0.05. Fail to reject the null hypothesis of no effect from the column factor. Conclude there is no effect from the column factor.